Okay, once again, if you want to download the slides that I'll be running through in this session, they're available at this bit.ly URL right now. I recommend you get them because there's a lot of data, a lot of rate distortion charts, a lot of tables, and a lot of frames for comparison purposes. So I'm Jan Ozer. I'm a contributing editor to Streaming Media Magazine. And the problem we're looking at solving today is hardware transcoding in the cloud. So I think the optimal workflow for a lot of live producers is to send a single efficient stream into the cloud and transcode there to either H.264 or HEVC. And what we're going to look at here are solutions for doing that, both hardware and software. So we're going to look at both H.264 and HEVC. It's all transcoding in the cloud. This is not a VOD class. This is more how you produce live events most efficiently using transcoding in the cloud. So here's the agenda for this class. It's an hour long. We've got 97 slides. I'm in a hurry. I want to cover what you will learn, the theory of testing, and then we'll look at H.264 results, including NVIDIA, Intel QuickSync, and then kind of the baseline, X.264 medium and very fast. And then we'll look at HEVC, and there we'll cover, used to be the NG codec solution, now it's the Xilinx solution. We'll cover Intel SVT HEVC, which is not really hardware, but it's kind of topical because it's newly announced and it's from Intel. And again, as a baseline, we'll look at X.265 and both medium and very fast. And this is available, this article published in September, and it's available on the Streaming Media website. And most of what I'm covering today is in that article, but you're getting a lot more data. Because you're getting 50 or 60 pages of, again, image comparisons, rate distortion charts, and data that we just couldn't put in that article. So what will you learn during this session? Well, there's three things I'm trying to tackle. One is the whole H.264 side. If you're choosing an H.264 transcoder, what are the options? How do they perform? And then the same thing for HEVC. What are the options? How do they perform? And then also, the methodology for analyzing different technologies. So we went through a lot of planning and a lot of time, and what I tried to do in this presentation for both of these categories here was to identify the hourly cost of the transcoding, the quality, both average and any kind of transient issues, and also stream consistency. Because if you're transcoding in large quantities, you really want a CBR stream because sudden spikes in the stream can really damage smoothness of distribution if you've got closed pipes on your CDNs. So this is, those are the areas that I focused on. And then also how to apply objective quality metrics to the quality analysis. How to find an inexpensive source for subjective evaluations. And how objective and subjective results can vary. So I do a lot with objective quality metrics, and I'm comfortable if I'm looking at I'm trying to identify the best preset for X.264 or the best keyframe interval for a particular file. I'm comfortable using objective metrics for about 99% of that. If I'm comparing codecs, I always want to look at the subjective side as well, because codecs are so different in how they handle things like rate distortion and how they trade off psychovisual optimizations that may reduce their scores but actually increase visual quality, that if you're ever going to compare codecs, as we're doing here, you need to at least consider some objective evaluations. There's a service I'll talk about called Subjectify that we got. You basically upload your files to them. They do online distribution to their testers. Their testers make $2 for 10 minutes. There's checks in there to make sure they're not just pushing boxes. So we got 400 or 500 results, comparisons for under $200. So from that perspective, the comfort that gives me in either verifying the results or showing where the results might be off is really invaluable. So if you're going to do any kind of comparison between codec, I would urge you to at least take a look at getting some subjective confirmations for whatever your key findings are. And then, why did we test? I covered this a few minutes ago. Cloud transcoding is the optimal workflow for many live producers. There's two options, hardware and software. Software requires an expensive cloud computer with lots of CPUs. Hardware is cheaper and is higher performing, but how do they compare from a quality perspective, from a cost perspective? And what did we learn? Quality-wise, hardware stacks up pretty well. And we saw that with both H.264 and HEVC. And from a cost perspective, it's complicated. I had hoped that I could find one cloud computer that could do all of the tests that I wanted to perform, so I could say, okay, on this system we could do one set of streams with this technology, or 5 set of streams with this technology, but we ended up having to go all over the map because we were looking at hardware-specific encoding machines. So I tried to give you some data relating to the cost per stream, but it's not as hard as I would like it to be. Not as, I guess, accurate as I'd like it to be. Okay, so the theory of testing that I adhere to is, first I want to derive the most practical encoding combination. I don't always want to test at the highest possible quality. I want to test at the quality level and performance levels most producers would want to use. And then we tested the capacity using an encoding ladder. You'll look at it in a second. So the first thing we wanted to figure out was, what are the right settings? Then at those settings, how many encoding ladders could this solution produce? On this particular system, because that's how we got cost per hour. So if a system cost us $1 an hour and we could produce 2 full encoding ladders, the cost per hour was 50 cents. For hardware, we accepted no drop frames. For software, it was 55 frames per second or higher. And then we tested quality at those settings using all this stuff that you'll see, the rate distortion curves, BD rate functions, and I'll cover what these are when we get there. And then subjective comparisons via Subjectify, which is the service I just mentioned. One big issue whenever you compare technologies is tuning for metrics. So anytime you apply objective quality metrics to any encodes, you need to be conscious of the fact that a lot of the codec developers say you should tune for PSNR or tune for SSIM or tune for VMAF. And the reason you do that is because the psychovisual optimizations I talked about a few minutes ago, they can increase the visual, the subjective quality, but they can decrease benchmark scores because they're measuring the error in the file. So whenever you produce any kind of objective or subjective comparisons, you want to be sensitive to this. With H.264, there was no way to tune Intel QuickSync, so we didn't tune any of them. And we tested again, with objective metrics and with software. We'll look at those results when we get there. With HEVC, we created 2 sets of files. We tuned for the metrics, and then we didn't tune for the metric for the subjective comparisons. Why did we do that? Because we wanted to follow the codec vendor's advice at this stage, and then tune for maximum subjective quality at the second stage. And now we're going to start looking at the H.264 instances that we looked at and kind of the analysis that we went through with each technology. And it's the instance, the settings we use, the capacity, and the quality. So the instance, company called Softellum is the developer of Nimble Streamer. They have a lot of experience setting up NVIDIA transcodes. So they set this up for me on a G3.4 extra large computer. So this is an NVIDIA QuickSync transcoding computer that cost around $1.14 an hour. And then trying to find the optimal settings, this is what, here's the source of the settings. This is a white paper from NVIDIA. This is the recommended string that they produced in that white paper. I had concerns about using the slow preset because I thought that might unfairly limit the performance. And I also had concerns about a 2x buffer size, because 2x buffer size can increase the variability in the stream. So I wanted to test and see, okay, if I go to 5 megabits here and I go to the medium preset, what happens to performance, what happens to quality? So here I'm testing the 2-second buffer versus the 1-second buffer. this is the tool called Bitrate Viewer, and we see a little bit more variability in the stream here, which was my concern. And then at 1 second buffer, we see a little bit more consistent stream. And how did that impact quality? We'll look at that in a second. And then we tried the medium preset as opposed to the slow preset to get better performance. And what I found was that the VMAF score dropped from 82.35 with the slow preset to 82.19 with the medium preset. So we got a boost in performance with no real difference in visual quality. And then whenever you look at codecs like this, you want to make sure that you're not running the risk of transient issues. So this is the Moscow State University tool. The red is the white paper, what NVIDIA recommended. Green is the medium using the smaller buffer. And the question I was trying to answer here is, are there any transient issues that the new settings created? And this is, again, the VMAF plot. So these are the VMAF scores for both files over the duration of the test file. And it's pretty similar throughout. When I checked these frames in the interface, there was no visible difference in the frames. So the conclusion was we're good to go with the updated settings. And then here's kind of the analysis. Here's the settings we started with. So the bit rate was 3.7 megabits per second for this file, which is a 4 megabit per second encode. Peak bit rate, again, here we're focusing on variability. VMAF score, PSNR score, CPU utilization. CPU utilization didn't change that much. But we saw quality actually improve at the new settings, and we saw that maximum decreased a little bit. Performance really wasn't affected that much. Long story short, this is what we did to try and figure out the optimal presets for NVIDIA. And this is what we ended up using. So we went from slow to medium and from 10 megabits per second to 5 megabits per second. Fortunately, things got a little bit simpler from there. Now, I mentioned a few minutes ago that we wanted to test performance. We wanted to see how many encoding ladders could this solution produce on the instance that we used to run it on. So this is the encoding ladder that we produced. And then what we did is, again, how many simultaneous encodes can we produce with this encoding ladder? And we tested with one string open, then we opened up another instance and tested again until we stopped getting 60 frames per second. Intel was able to achieve 2 60 frame per second encodes on the G34 large. Okay, so you could get 2, on that machine, you could handle 2 live events at the same time, which obviously dropped the cost per stream. Okay, here's what we use for medium and very fast. Again, no tuning. And then for very fast, we just changed the preset from medium to very fast. And then from a capacity perspective, on the GPU optimized computer that we tested the NVIDIA on, we couldn't produce any full encoding ladders with the NVIDIA solution. So we went to a C5.18 extra large, which cost about the same, $1.25 per hour versus $1.14 per hour, and we got 4 simultaneous encodes, and that's what this looked like. So here we're seeing 58 frames per second, 58 frames per second, 57 frames per second, and 57 frames per second on the same machine. So it's definitely cheaper to go with the H.264 based solutions if you get a big enough machine. The problem is Intel keeps coming out with new hardware. So again, part of this is how did the systems perform? Part of it is when you perform your own analysis, what are you going to do to kind of come up with your own data? Okay, same factors we looked at for the Intel QuickSync, what system, what command line, and what preset and throughput. The system was this. We couldn't get a cost per hour because they only charge by the month. I know this is kind of a rough estimate of cost per hour, but that's the best I could come up with. Very few people are transcoding every hour, 31 days a month, 24 hours a day. Here's the Intel script that we started with, and this was given to us by Intel. And they had a bunch of different presets. They didn't recommend which one we used. So we ran through with the test file, how many frames per second do we get with each preset, and what's the VMAF score? And this is what this plots out like. So we see preset 1 is the slowest, highest quality preset. Preset 4, 5, and 6, you start to see quality. You see quality really go up here and then slow down. And you really don't see that much drop in quality at all. So Intel said, let's test with 4. So we tested with 4. So we used the preset 4 in all the tests we did with Intel. And one encoding ladder with QuickSync at preset 4, we could produce a full encoding ladder. We couldn't do 2 encoding ladders, not even with the fastest preset. So, sorry. Encoding ladder with QuickSync, we were able to get 1 full encoding ladder, but not 2. And with H.264, even using the very fast preset, we couldn't get 1 full encoding ladder. So if you're going to use H.264, you're going to need a pretty expensive computer. And we'll look at some price estimates when we get there. Then I wanted to look at data rate consistency. Again, I'm familiar with some of the large producers who are sending out live streams in the hundreds of thousands of streams, and they work very close to the capacity of some of their CDNs. So if you have a big spike in data at some point in the stream, you can actually swamp the CDN and lose performance. So some of the tests I've done for them are, how consistent is the stream? And I wanted to test. That's probably not going to impact most people. If you're small, if you're a small producer, you don't really care. But if you're a really large producer, you care a lot. And this is what it looks like. So this is the data rate for. We looked at 4 files. One of the files was a football game, and obviously that was the highest motion file, most variability. So what we're seeing is the 2 hardware solutions give us a much more compact stream and much less variability than we get with the software. So again, you may not care about this if you're distributing in the thousands or even tens of thousands, but if you're in the hundreds of thousands, this is important. And then kind of putting numbers to these graphs. The target data rate was 3 megabits per second. They all met those pretty easily. And then these are the standard deviations, which obviously reflects how much variability goes into the stream. And this is the max data rate that we found within that stream. So here what we're seeing is the Intel QuickSync had the lowest fluctuation. It had the lowest max data rate. So in terms of my analysis, this was number 1 in this category, number 2, number 3, and number 4. OK, quality results, we looked at 4 clips. The Netflix dinner scene clip, Harmonic has a football clip that we used, Grand Theft Auto video, and Netflix Meridian, all at 1080p 60. And as a reminder, we tested 4 codecs for H.264 conversion. And here's what the rate distortion curves look like. So for this is dinner scene. What we're seeing here is NVIDIA is close to the top. QuickSync is close to the top. Medium is very close. And very fast is clearly not competitive. And this is, again, the Moscow State University tool. What I'm looking for here is, are there any transient issues? And I looked at the best and the worst. The best was NVIDIA. The worst was very fast. And we're seeing no downward spikes that would indicate any quality differences. So even though we have a huge score here, this would, we're seeing a drop from 76 to around 80. A just noticeable difference for VMAF is around 6 points. You wouldn't expect to see a visible difference. And this kind of confirms it. Even between the best and the worst, nobody's going to notice the difference. And again, red is the NVIDIA, green is very fast. And then we computed the Bonnard functions BD rate numbers, and basically what the with the BD rate, these are the 2 rate distortion curves. This is, say, lowest quality, this is highest quality. What BD rate tells you is at this quality level, how much data rate do you save with this solution. And we're going to look at what those numbers look like in a second, but I just wanted to explain what BD rate talks about. I got the stats using an Excel plugin that's available for download here. And you can download that and use it. There's an article. This is an article I wrote that includes both the download link and also how to use it. And then here's the ratings that we produced for the dinner scene clip. Okay, and I'm gonna, this was 1, NVIDIA was 2, so NVIDIA was 1, QuickSync was 2, H.264 medium was 3, and very fast was 4. This is VMAF, and this is PSNR. I believe in VMAF more than I believe in PSNR, but a lot of people like to see PSNR numbers because they're familiar with them. And again, you have all this available for download now, so I'm not going to go through each one in detail. Here's the football clip. This was the hardest clip. Again, what we see is the NVIDIA is first, closely followed by H.264 medium and QuickSync, and then down here is very fast. Down here we're in the 53 to 62 range. We're seeing a little bit more stream variability as we saw in dinner scene. So NVIDIA is in red, very fast is in green, no real big downward spikes. And if you look at the clips themselves, so what I would do here is I'd go to an area like this or an area like this where there appears to be a lot of difference. And then I would look at the actual frames. And here's the source frame, here's the NVIDIA frame, and here's the very fast frame. So again, this is source, NVIDIA, very fast. And you can see a bit of difference, but it's not striking. You're not seeing excessive blockiness. You're not seeing significant error. So I would say NVIDIA is slightly better, but I'm not seeing, and that was true for the entire clip. And again, here are the ratings. NVIDIA was first, medium was second, QuickSync was third, very fast was fourth. Slight difference in the PSNR side. Here's Grand Theft Auto video. This is a completely different type of clip. This is a synthetic computer gaming clip. And what we saw here is NVIDIA and QuickSync are very close together. H.264 starts pretty slow but catches up at the high end. And H.264 very fast, can't compete. Here are the ratings. And then looking at visual differences here, Intel is in red, very fast is in green, and this is the source. This is Intel. So we're seeing a lot of loss of detail, not a lot of artifacting, but when we look at the source, Intel, very fast, we start to see significant differences. So this is an example of where the difference in technology will yield regions in the clip that actually a viewer might notice and might be degrading the quality of experience. And then here's Meridian. This is a pretty easy to encode clip. We see QuickSync, NVIDIA, medium, very fast. Once again, are we going to find any errors here? So these frames look suspicious. Let's see what they look like. And here we're comparing Intel to very fast. And the issues are very transient. The spikes are very narrow, which means it's only 1 or 2 frames. And this is the source frame. This is Intel. And then this is very fast. So here you would say, OK, I can see the difference in this one frame, but what's the likelihood that somebody watching this, this is probably a 3-frame sequence. So before, with GTAV, there was a very significant difference that was over a much longer period. I would look at this and say, very few people are going to notice this. The Meridian clip has a bunch of stuff Netflix put in there to identify errors like this. But this is only, the flashing sequence is probably only 2 or 3 frames both ways. So they're flashing from light to dark, and that's what causes these problems. So again, would somebody notice the difference here? Probably not. And then here's the overall numbers for VMAF. And we've got NVIDIA with a slight lead, QuickSync. Nobody's going to notice the difference qualitatively here. And as we saw, not so much there either. And then here are the BD rate numbers. Overall, NVIDIA was first. What these numbers mean is that NVIDIA can produce the same quality as QuickSync, and reduced the data rate by about 3%. NVIDIA versus NVIDIA is the same. NVIDIA can produce the same quality as X.264 medium at around 4.75% lower data rate. And NVIDIA can produce the same quality as X.264 very fast at 27% lower data rate. So that's what those numbers mean, and they mean the same for PSNR and VMAF. They're just, obviously looking at different metrics. So those are the objective metrics. Here's Subjectify. So it's a service from the Moscow State University that recruits viewers to compare video or still images. And you send them the test files, they recruit the viewers to run A/B tests, which video looks better of these two. And the cost is about $3 per viewer who can compare 10 20-second A/B comparisons per session. So there's only about maybe 5 minutes of video that they can look at. They earn $3. It's not terrible. The work done for this article, which again I think was around 500 different viewers, was around $300, which was paid for by Encoding and Intel. And the website is Subjectify US, and I wrote a review of the technology you can look at there. And here's the results we got back. So, and this is the overall ratings. They rated each clip individually. And what we saw was that QuickSync was slightly higher. So QuickSync is Intel, NVIDIA is NVIDIA. They came in second, but the difference is very, very limited. X.264 medium came in third, and very fast came in a distant fourth. So what did this add up to overall? Here we see the cost per hour on top, stream consistency we covered, VMAF quality rank and PSNR quality rank. Interesting that these two switched, but the numbers were pretty close anyway. And then subjective quality, we see 1, 2, 3, 4, probably not a surprise. So this is an instance where the subjective quality was actually pretty close to what we found with the objective quality. And overall, you can kind of rate these either way. I mean, QuickSync was a little bit less expensive than NVIDIA. Either of those solutions would be fine. Didn't notice us. But those are the rankings in terms of the different categories that we followed. Any questions about H.264?
I might just be ignorant about QuickSync and NVIDIA, but are those just software solutions in the cloud, or are you saying they're actual hardware? I missed that.
Good question. So the Intel, so the question is, what's the difference between the, is QuickSync and Intel on hardware or software? And they are both in hardware. So you can only run the Intel QuickSync on specific processors. So you have to get an instance that has those processors. And with NVIDIA, you need an instance that's got the hardware CPUs, the, what's their big, the NVIDIA hardware. There's an acronym for it. Pardon?
2080 RTX.
One more time?
2080.
No, it's more. CUDA, that's what I was looking for. It needs the CUDA hardware on there. But they're definitely hardware solutions. Won't run with the with the stock version of FFmpeg. If you set it up yourself, you need a GPU instance on the Amazon cloud. And then they're using the hardware on that device to transcode, which is how they get their efficiencies.
But you're not necessarily saying on-prem. You're just saying in the cloud with certain dependencies on the GPU.
Yeah. So anything we're doing here on. You can get the hardware in-house if you want to do it there as well. Either way, if you have the hardware with those transcoding capabilities, you're going to get the results that we saw here. I wanted to do it in the cloud because, again, from a live workflow, it seems to make the most sense to do it in the cloud because then you've got one stream out and then you can distribute it very easily. But if you want to do it in-house, you can do it as well.
So the counter of that question is the very fast and X.264 medium, is that software or hardware and software?
Okay, I'm sorry if I didn't make this clear. So what we did was we looked at, so let me go back to, well, here we go. This is hardware. This only runs on whatever the CPUs or GPUs are from Intel that have the CUDA technology. I'm sorry, this is Intel. This needs a specific Intel CPU. This is NVIDIA, it needs a specific GPU. You can get them in the cloud, they're available on cloud instances, or you can buy the hardware yourself. These are just stock versions of FFmpeg. So this is just upload FFmpeg to the same instances we tested these guys on and make sure we were running the version of FFmpeg that you could download at any point.
Those are just running on Xeon processors.
Say it again?
They're running on Xeon processors, just generally.
I have the systems listed in the notes, and I don't know if they were Xeons or not. These are what I wanted to do was to just come up with pretty generic cloud instances, because that way anybody could price the per hour. But the more you got into the hardware, the less available they became on AWS instances that you could actually price per hour. And even on the Intel solution, that turned out to be the case. They had to send me to a smaller cloud vendor. But again, this needs a specific CPU. This needs a specific GPU. These run anywhere. I can take one more question before we get to HEVC.
I just had a quick question, Jan. When you were showing the X264 encodes, you were using the real-time parameter in front of the input, so you were forcing it to only play out like it was like VOD was live, and that was intentional, I presume?
Yeah.
So that, okay.
And so I tried to listen to the vendors when I could. I mean, everything happened in real time. We were tracking that. But if you don't use the RE, you're testing capacity. If you don't use the RE, the FFmpeg will convert it as fast as it can. So it'll convert it 100 frames per second. So, and it'll do one, and then you try to do another one, and it may or may not work. So we did the RE because we felt that was the best way to. When you put RE in the command string, that tells FFmpeg to do it at the frame rate, to convert at the frame rate of the video that you're working with. Okay, so for HEVC, we tested 4 solutions. These are base software-only solutions you get with any version of FFmpeg. This is Intel SVT HEVC. This is open source software. Doesn't require any. You may want to check what you need to run SVT, but it's a software-based solution. I think it runs more efficiently on some Intel hardware devices, but and you may have to have a specific CPU to run. Anybody here from Intel? Do you know what you need to do with SVT?
Skylake for higher.
Say it again?
Skylake or newer.
Okay, so it needs to be a specific Intel processor.
It won't run on anything, but it runs best in Skylake.
Okay, thank you. And then this is FPGA based. So this requires a specific hardware, so it's programmable hardware. Encoding was the company that developed it. They developed it using Xilinx hardware, and sometime in the last couple of months, Xilinx bought Encoding and the rights to the product. So this one will run only on an FPGA, which means you have to buy a specific instance with FPGA, but that's pretty simple on the Amazon cloud at this point. Runs best on the specific CPUs they mentioned, and these are both just regular off-the-shelf FFmpeg runs on anything. Okay, the Xilinx computer, we had this CPU. We had 2 FPGA boards on the system, and we were able to produce 1 full encoding ladder for each FPGA. And we'll cover costs when we get there. The Xilinx Script, and this is pretty typical with hardware. There's no preset to toggle for quality versus encoding speed. They just produce the best quality they can until they just can't produce in real time. So Xilinx is like that. Some other technologies I've looked at are like that as well. From a tuning perspective, we produced the HEVC technologies 2 ways. One for objective testing, one for subjective testing. For the objective testing, we turned off adaptive quantization per Xilinx. So this would be the script for subjective testing, and for the objective testing, we included this. Is that clear? And then we tested on an FPGA-based solution from a service called Altered Silicon, 2 FPGA cards. It cost $2.21 per hour. We were able to produce 1 encoding ladder, but Xilinx, then NG Codec, said they should be able to get 2 streams per FPGA by right about now. After the acquisition, we just had trouble getting this confirmed. So if I was going to look at the NG Codec Now Xilinx solution, I would confirm these performance claims. I was only going to get one encoding ladder per entire device. They say you should be able to get 2 per FPGA, and since the device has 2 FPGAs, you should be able to get 4 per card. But I wasn't able to confirm that.
What do you mean per hour? Is that like a service fee?
No, so the question was, what do you mean per hour? What I mean per hour is, I wanted to normalize the cost in some way, so I looked at per hour of transcoding. So we started off defining the encoding ladder we're using for test purposes. If you could produce 1 encoding ladder per hour in real time, this would cost you $2.21 per hour to run. If you could produce 4 encoding ladders, this would cost you, roughly 60 cents per hour per live stream. Because when you produce your live streams, that's what you care about. You care about what's it cost me to transcode on the cloud. Okay, what is SVT HEVC? This is scalable video technology for HEVC, also AV1, I think also VP9, and I have the answers here. It's Intel scalable processor and the Xeon D processor. So if you want optimal performance, these are the processors you would get. You can get more information here, and basically it's a highly efficient codec for multi-threaded operations. Intel's, they're not moving away from hardware. They're still supporting the QuickSync hardware, but they bought a company that produced the SVC technology that they feel accelerates the production of all codecs. So they're kind of moving in that direction. So there's an SVT AV1, there's an SVT HEVC, and I believe there's an SVT VP9. So Intel's technology for high performance transcoding. Which preset for Intel? Here's the presets, here's the VMAF score, here's the frame per second. So the presets are down here. We could go from 1 till 10. And then this is the high quality option, low performing, 26 frames per second. This is the high performing, lower quality at 73.8. And then Intel basically said, looking at this data, let's just test at preset 6. So that's the preset we tested with. And here's the Intel script. This was provided by Intel. And then there were 3 tuning mechanisms that we used. One is you tune 0 for subjective quality, and that's what we see up here on the command string. If you're producing for PSNR or SSIM, you would tune 1. If you're producing for VMAF, you would use 2. And this is what we use for VMAF and PSNR. We didn't want to do 3 different encodes for Intel. We did 2. 1 for visual tuning, which we checked with Subjectify. 1 that we use for the VMAF and PSNR scores. And we tested on a C5.9 extra large system. With that processor, we were able to get 2 simultaneous encodes of the full encoding ladder using preset 6, tune 0. Spot pricing was $346.6 per hour. So the cost per ladder for these 2 ladders was about 17 cents. In comparison to the 221 we actually got with the FPGA board. For H.265, we kept the script as simple as possible. Here's the ORE that Robert was referring to. This tells it, encode in real time. We changed the medium preset. This is showing the very fast. And we tuned for PSNR for objective testing. And For X.265 capacity and cost, we tested on the same system, and we produced no full encoding ladders on that system. So I think X.264 is pretty efficient. You can find a cloud system that'll run it. If you want to transcode X.265 in the cloud, you're going to have to spend a lot on hardware. You're going to have to get a really powerful system. Okay, data rate consistency. This is kind of interesting. Again, we had the hardware solution. The only true hardware solution was Encoding, now Xilinx. And we see that the bit rate is much more compact and much less variability than we see with the software solutions. Encoding, we saw the lowest fluctuation, the lowest standard deviation. We saw the lowest max data rate. So I rated Encoding first, Intel second, X.264 very fast third, and X.265 medium fourth. So this is data rate consistency. We encoded a 3 megabit per second football file that had a lot of stream variability. Same for Eclipse. For our rate distortion curves, for H.264, we tested from 2 to 5 megabits per second. For HEVC, we tested from 1 to 4. And again, the 4 tested codecs. This is dinner scene. And what we're seeing, X.265 medium, NG codec, SVT, HEVC, and then very fast. The problem with X.265 medium and all of these rate distortion curves and BD charts is it's like the stuff at the delicatessen you can't buy. I mean, X.264 medium looks great, but we couldn't find a system that would produce it in the cloud. Doesn't mean it's not there, but you're going to have to spend a lot of money to produce the medium preset where you can get pretty effective price points with other technologies. So I put X.265 medium in there, even though we didn't produce it in real time. But keep in mind, it's probably going to cost a lot more to produce. Are there any actual visible differences? So here we're seeing Xilinx is up there, Intel, and this is the dinner scene clip. And this is like, holy cow, something's going on here. That's a frame that you want to look at. When you look at a frame here, you see this is green, this is red. So both of them have pretty low quality, but it really looks, well, I guess it's the same thing here. But this one would give you some pause. And this is one of those scenes where even though there's a really big visual difference, so this is the source, this is Xilinx, this is Intel. So Xilinx is the bad one here. But because it's such a busy scene, you just don't see it. If you looked at the frames, here's the source, here's the Xilinx, here's the Intel, and all across you can see it. Here's the source, here's Xilinx, Intel's a little bit better. You'd never see it in real time in the context of this particular sequence. So here's the quality rating for dinner scenes. And again, X.264 medium was first. NG codec was second. SVT HEVC was third. And then very fast was last. Here's football. Again, medium. Down here, at the lower range of the scale, we're seeing very fast and NG codec. And then SVT HEVC is the lowest performing there. Are we going to see quality differences in the clip? And we're seeing Xilinx in red, Intel in green. And you're not seeing huge differences here that would alert you to try and look. This is the source. This is Xilinx. This is Intel. So this would be in a range like over here or over here. And you're just not seeing significant differences that jump out. We saw with the Grand Theft Auto clip at the H.264, we saw huge differences that were like, holy cow. We're not seeing that with these clips. So here are the numbers, and I'll spend more time on the total numbers. This is GTAV. X.264 medium is first. NG codec is second. X.265 very fast third. SVT HEVC is fourth. Are we going to see qualitative differences here? Xilinx versus Intel. And this is Grand Theft Auto. This is the source. This is Xilinx. This is Intel. You do see a slight quality loss, but you're not seeing anything that's really, dramatic. And then Meridian, same structure. We're seeing medium first, NG codec second, very fast. I'm sorry. Very fast and medium, very fast in SVT. Are there any actual visible differences? This is really scary. So you look at the clip, again, it's the spot in the mirror. This is the source. This is Xilinx. Thank you. It's my one joke in the entire. And then here's Intel. So you see a very significant difference there in this one spot. And then here's the BG rate functions, and here's overall numbers. Again, may not be accessible, but it's clearly the quality leader. NG codec does a really nice job. X.265 very fast is here, and SVT HEVC is there with preset 6. So 1, 2, 3, 4, and 1 is the same, 2 is the same, 3 is the same, 4 is the same. Same result, both metrics. What do we get with Subjectify? This was one of those instances where, why did I say test subjectively with different codecs? Because here we're saying NG codec was second, and it's second, so what we're seeing here is X.265 medium can produce the same quality as NG codec at a 10% lower data rate. So it's a pretty substantial advantage. 10% is a pretty big number. But if you look at the subjective ratings, what you see is NG codec came out first by a pretty significant margin overall. So this is a Xilinx project. The only concern about Xilinx was that one transient quality issue we saw in that one Netflix clip. That's something I would want to follow up on. But from an overall quality perspective, this came out really well. So again, how much variability do we see between subjective and objective? We saw 2 here, 3 here, 1 here. The rest are actually reasonably close. We're seeing 1 stop difference in all. But this is why I always want to look at subjective quality differences if I'm comparing compression technologies. Transient issues were a concern for the Xilinx solution, which also produced the best stream consistency. I checked with Intel about 6 weeks ago to ask if they had any updates to this technology to try and get more recent testing, and they didn't have anything at that time. It's SVT HEVC is a new technology, or relatively new. I think it's going to advance over the next 6 to 12 months. And as I said at the start, I want you to understand the methodology as much as the individual results. This is the type of testing you should do if you're going to try and identify the best transcoding solution for your cloud operation. So here's the procedure. You want to test capacity using your current encoding ladder to compute the cost per hour. You want to test quality using 4 files at relevant intervals. Performance quality graphs. You definitely want to look beneath the numbers. You want to get the Moscow State University tool or the Sim Plus VOD monitor that lets you plot the quality over the duration of the video clip and then zoom in and see what the frames actually look like. If you're comparing different codecs, I strongly consider getting subjective evaluations as well. It's very inexpensive, and I just think it's very worthwhile as a reality check as compared to all the objective metrics. Okay, any questions? Hang on one second. Let me make my partner back there work.
I'm pretty loud.
It's the here, up here, Robert.
You wanted? Oh, this guy over here. Sorry.
So during the setup of one of those tests, it looked like you were passing two different input files for subjective versus your objective measures. Like, I'm kind of intrigued by the decision behind that, because you're not going to feed, you know, it feels like you'd overfit, I guess, is my concern. Like, what happens when you just give the subjective evaluation the same file that you were giving for your objective scoring?
I mean, the whole tuning issue is just a very sensitive issue in the codec space.
Yeah.
And so from my perspective, it's a challenging issue. And if you look at what do people do in the space, if you're an academic and you're evaluating new compression technologies, you always tune. Because if you don't, the codec vendors will scream at you. If you are Facebook or you're Netflix, you produce using whatever parameters you use for your final encode. So, but I wanted to publish the results, and I also wanted to use subjective and objectives. It's really not that big a deal. I mean, to encode your clips is probably, once you get the final command strings done, it's probably 10 minutes work. So send off one set off to subjectify, one set off into your metric analyzer. And so it's not that hard, but if you're going to publish something, either you need to be clear on what you're doing and why. And from my perspective, I thought it was more appropriate to tune.
You initially said what medium preset is actually can't produce a single ladder, right, for speed.
The medium preset couldn't produce a single encoding ladder. That's correct.
Yeah. So is it fair to compare medium with others, because it's looks like medium from other different categories? It's a higher quality level, but speed is.
You know, it's a great question. The problem, and I thought about leaving it out, but there were two realities. Number one, there's going to be a machine out there that can produce medium. So if I kept testing higher and higher machines, I probably could have found one. Number two, everybody you talk to is going to want to know, how does it compare to H.265 medium? Because that's kind of the benchmark in the industry. So I felt it was appropriate to test it. And then, you know, with the caveat that it's going to be very expensive. But I did, you know, everybody wants to know how it compares to medium. And that's why we did both medium and very fast.
So the frames you use for comparison are iframe or keyframes or not?
I'm sorry, say that again?
The frames you use.
Yeah, so we made sure the GOP sizes were all the same. We made sure that the frame rate's 60 frames per second, but it was 2-second GOP sizes, and so iframe every 120 frames. Did that answer your question?
Yeah, I'm just wondering the frames, like you specify, okay, compare like for the same frame, right? You compare the results, like the MF or PNSR. So I'm wondering that frame, specific frame is iframe or not iframe?
I didn't. Good question. I didn't look at that. We just, you know, they should be pretty synchronized, because these were files that we transcoded at identical encoding parameters, so the keyframes should have aligned, but I didn't make sure that was the case. You know, I went into the different visualization tool I had. Whenever there was a big spike in quality, that's where I looked. Any other questions?
Is there a reason you didn't evaluate the NVIDIA HEVC encoder that they have now on their dies, their more recent dies?
No, didn't. I reached out to NVIDIA and just never heard back. And then and really, when I test technologies like this, I don't want to say never. I heard back very close to the time I was actually, you know, it took like 4 weeks, and I don't want to test a technology that I don't get support from the vendor, because then the vendor's going to say, well, you should have done this. And, you know, I had their white paper with the other one, and NVIDIA just hasn't reached out a lot. You know, you test what you know, and Intel just came out with the SVT, HEVC, and I knew the NG codec guys, so it wasn't a solution I was familiar with. The company didn't either promote or support my efforts, and you know, and those are the reasons.
I have two questions. What was that tool you were using to compare like the red and green?
That was the Moscow State University Video Quality Measurement Tool. So if you Google MSU VQMT, you'll be able to find it pretty quickly. If you add my name, you'll be able to see my review of it.
Okay. And it seems like a lot of the resources you were using were in Amazon. Have you ever done any testing with their media services, like their media, Elemental Media Live, or any of the transcoding they have in the cloud?
Good question. I haven't. The presumption here was that people were going to want to. I guess the theory of the article was, and the presentation was FFmpeg. You know what you can do in FFmpeg with hardware and software. So
Gotcha.
you know, AWS Elemental is obviously very credible, but we didn't look at any vendor-based solutions, application-based solutions in this.
Gotcha.
Anybody else? Okay, thank you for your attention.